Welcome to FRB 2021 primer talk on FRBs measuring their properties. My name is Jerry Ng. I'm a postdoctoral researcher from the University of Toronto. A bit about myself. I work with the CHIME FRB collaboration. So I apologize in advance. Many of the examples I'll be using in this talk come from CHIME. There's definitely a bit of a personal bias, but I've tried to include other groups' results as far as I am aware. So you've found an FRB. Congrats. Or maybe you have some FRB data on hand. What can we measure from an FRB observation? Here is a gallery of some randomly selected fast radio bursts from the recently published CHIME Catalog 1. By eye, we can already see that FRBs have diverse morphology and there are rich information we can obtain from these data. I have on the left a list of key parameters we can measure from FRB observational data. We'll be going through each of these parameters. I'll be discussing these terms, what they are, how to measure them, and what are the current state of the art regarding these parameters. And some of the things we'll have to pay attention to when quantifying them. Hopefully this talk will help explain some of these terms we'll be hearing a lot throughout the conference. Note that in this talk, I will not be discussing the astrophysical application from these measurements. Instead, I'll refer you to Manisha's primer talk on this exact topic. First off, localization. With your FRB data, you probably have some rough idea of where the FRB comes from. I won't talk about individual localization here, since there's a whole other primer talk by Sherry about it. Overall, if you have a good sample of many RA in deck, for example, as shown by the CHIME Catalog 1 paper, we can quantify sky distribution of FRBs, study any dependence with other parameters such as galactic latitude. A somewhat related derived quantity from this is the all-sky rate. Assuming an isotropic FRB distribution using the total time on sky and the area of sky covered by a particular survey, it is now a standard practice to extrapolate the discovery rate to the entire sky. Currently, most of the studies show FRB event rate of about 1,000 per sky per day. Next is dispersion measure. This is probably the one most important parameter of FRBs. It is also what this artistic impression is trying to show on the left. FRB signal is dispersed by the free electrons along the line of sight. As a result, the high energy blue end of the spectrum arrives the observer first, then comes the medium energy yellow waves, and finally the lowest energy red end of the spectrum. On the right, you can see the signal of the first ever detected fast radio burst, also known as the Lorimer burst. This is a waterfall plot with frequency versus time. The thick black line is the FRB signal. If I were to recolor this figure with the same color analogy, you can see now how the high energy blue end of the burst arrives at an earlier time compared to the lower energy red end of the burst. The amount of dispersion delay is proportional to the observing frequency to the power -2 and the integral column density of free electrons along the line of sight. This is to say that dispersion delay is largest at lowest frequency. For example, at the observing frequency band of low-FAR between 100 and 200 megahertz, an FRB with a relatively average DM of say 350 units will have a dispersion delay of about 80 seconds, which means it takes over a minute for an FRB to pass through the observing band. DM can be obtained either with the pulse-feeding algorithm or by the search code directly out of the box. Typically, we can obtain a precision of about 0.1 parsec per cubic centimeter. One side note about this waterfall plot, which you'll be seeing a lot in the FRB talks. Here in this particular example, the dispersion measure is deliberately not fully corrected. So we can see the way the burst is dispersed. But most of the time, people will show the dispersion corrected plot where there is no more time delay, and so the FRB will appear as a straight vertical line. This is so that we can focus instead on other aspects of the burst morphology. DM is a very defining parameter of FRB, since it is mainly how we know that they are extragalactic in nature. As said, DM is proportional to the free electron density, which is also a proxy for the distance. On the left, this is a plot of the DM versus galactic latitude. The black dots are pulsars, which are mostly in our galaxy. Their DM trace the shape of the Milky Way with the highest electron density along the galactic plane. In comparison, FRBs are the blue dots, and they have much higher DMs relative to pulsars for a given galactic latitude. This is the best evidence that FRBs are extragalactic in nature. As of now, you can see from the histogram on the right, currently FRBs have been detected to have DMs ranging from 88 to just over 3,000 DM units. Despite the well-quantified DM equation, there can be nuances when it comes to measuring this quantity. Here's an example of an FRB which happens to have very particular microstructure. So by dispersing the FRB over a range of DMs, these structures are being aligned slightly differently. By eye, I would have said that the middle panel is a good alignment of the microstructure. Now, however, the associated DM from this alignment is here, which is actually not where the highest signal to noise is. The highest signal to noise here comes from this particular DM when the microstructure is aligned in such a way. So when talking about DM, we should be mindful whether it is being optimized for structure or signal to noise, since the result, as you can see, can be different. Things can be particularly complicated for multi-peak bursts. Also, small amounts of DM variation can exist, for example, for a repeating FRB. So DM might not be a unique identifier for an FRB. Width of the burst is another useful parameter. Basically, how long does the burst last? To first order, we can fit a top head function to the FRB, and we'll get a so-called boxcar width. On the left, you see a plot of the boxcar width of the 500 time catalog 1 FRBs. They have widths of up to about 100 millisecond or so. Now, this boxcar width is not the intrinsic width. As denoted in this equation, what we measured, apart from the intrinsic width, has got all this other stuff, including the sampling time, the dispersive delay across an individual frequency channel, its error, and also the scattering timescale, which we'll talk about in just a moment. Things get more complicated when the burst is not broadband or consists of multi-component structure. There are some existing software available we can use to model this intrinsic width. One example is the fit burst code used by Chime, which employs a least square fitting algorithm. On the right, you can see the same sample of FRBs and their model-fitted intrinsic width. The majority of FRBs have microsecond to millisecond width timescale. This is really short, and this is also why they are known as fast radio bursts. One thing to bear in mind when measuring burst width is that the resolution of your data can affect the measurement. Here are two examples of how the same FRB can look different if you have different level of time resolution. Say if you have data that has a sampling rate of 1 millisecond, this is the FRB you might be seeing, and you might think that this FRB is pretty wide in width. However, in high resolution data, as shown on the left, this is the exact same FRB, but just seen with the higher resolution, we see that the burst actually has multiple peaks. It's got a lot of structure to it. It's not just one wide burst. And this is the same for this other FRB here, low resolution data, high resolution data, and it looks quite different. Burst width measurement rely on correctly the dispersed data, as we discussed earlier. We need high time resolution data to resolve the burst structure to differentiate between multi-peak bursts versus one wide burst. And we also need to be careful when disentangling other broadening effects, such as frequency channel smearing and scattering. Scattering and scintillation are multi-path propagation effects due to turbulent plasma in the interstellar medium. Scattered radio waves arrive at a delayed time, resulting in a broadening of an otherwise intrinsically sharp pulse. You can see an example here in this top plot. The typical broadening in a scattering case is this one-sided exponential tail to the right, whereas scintillation is fluctuation in the observed intensity, as you can see in this bottom plot, just like the twinkling of stars caused by the Earth's atmosphere. Both of these timescales are proportional to the observing frequency nu to the power -4. And it's inversely proportional to the scintillation bandwidth delta nu. This effect is most prominent at low frequency. For example, a scattering timescale of about 50 milliseconds is expected in this low-far FRB at 150 megahertz observing frequency. And as you know now, this can be a rather significant fraction of the pulse width. In chime, when modeling an FRB, we run fit burst twice, once with a set of parameter assuming no scattering, and another time with a set of parameter including scattering. We quantified the presence of scattering by comparing which of these two fits is a better one. Still, it can be difficult to disentangle intrinsic broadening, scatter broadening, subpulse drifting, and any other secondary effects. Here is the plot again from the CHIME Catalog 1 paper, which we can see the distribution of scattering timescale of the 500 FRBs. Most of them, the scattering timescale is small. However, we do see evidence of a population of highly scattered FRB with scattering timescale more than 10 milliseconds, most of which are not detected by CHIME. I'll refer you to Pragya and Caitlin's talks on Wednesday for more detail. Another useful parameter of FRB is the spectral index and the running. Here are two examples of FRBs. This one on the left looks to be very broadband in frequencies, while the other one only has a partial bandwidth occupancy. In order to quantify these kind of differences, we can use an empirical spectral model with the power law function with spectral index alpha and spectral running beta. A broadband burst is when beta equals 0, as represented by the green line here. On the other hand, a narrowband Gaussian-like FRB would have a beta of less than 0, lighting up only partial part of the band, as shown by the orange line. So what about the overall distribution? Using the large sample of FRBs from CHIME's Catalog 1, we have shown that repeated bursts, the orange one, they tend to have narrow bandwidths and a Gaussian-like spectrum, which means the beta value tends to be less than 0. Whereas the one-off bursts, the green one, they tend to be more broadband, more power law-like in nature. Repeater bursts also tend to have wider widths. Roughly 30% of the bursts we detect are broadband and with single peak, while 60% of them are narrowband with single peak. Although some of those are most definitely due to beam response. What do I mean by that? Morphology and bandwidth occupancy can be entangled with beam response, especially when the FRB is not directly in bore sight. Here's an example of the magnetar FRB detected by CHIME. It was so bright that the FRB was detected in multiple adjacent beams on CHIME, the beams that are colored here. I'm showing 3 of those beams. The same FRB can look quite different in different beams. The top 2 beams appear to be broadband FRB, but in the lower beam, the lower panel, this FRB looks to be only with partial emission. Another note of caution is that the alpha and beta terms can certainly change for a given source. Here's an example of 5 of the repeated bursts of R2 detected on 5 different days. We can see that the repeated bursts could jump around, lighten up different parts of the spectrum each time and have different morphology. Moving on, another feature that has been seen in repeating FRBs is a downward drift in the burst frequency. This is also known as the set trombone effects. The plot I have here is a spectacular example of this effect seen in R3. I know at least one open source software that can be used for measuring drift rate, and I've linked it here. Note that in order to detect and measure drift rate, high time resolution data is once again needed, because otherwise you would just see this as a very wide burst. Joseph et al. Showed that drift rate of a particular burst, in this case R1, seemed to vary linearly as a function of observing frequencies across multiple telescopes. You can see more examples in Caleb and Pastor Marazuela. Overall, we see linear drift rates of few tens megahertz per millisecond. Currently, FRBs have been detected by at least 12 telescopes, spanning an observing frequency from 110 megahertz to 8 gigahertz. But again, a note of caution is that FRBs can be extremely band limited in some cases. This example here on the right is an FRB detected by the ultra wideband receiver at Parkes. And it only showed up at a tiny region of 65 megahertz out of the entire 3.3 gigahertz bandwidth. Changing gear a little bit to the signal to noise and fluence. Now, if we can calibrate the observing system, we can obtain a flux measurement from the signal to noise. In FRB astronomy, people tend to quote the fluence. So fluence is the integrated flux, essentially the area under the burst curve in the d-dispersed time series. Fluence is a more direct measurement of the energy of a burst because it describes the total flux generated over the duration or the width of the burst. Flux and fluence tend to be lower limits because in the case of uncertain localization, we have to assume that they are bore-side detections. Fluence of an FRB can vary a lot as well. Here I'm once again using the example of the magnetar FRB, whose fluence has been detected across 7 orders of magnitude by CHIME, STARS-2, Westerbrook, and FAST. And this FRB, or this magnetar, looks like it can bridge the luminosity gap between FRBs and pulsars. What about polarization? If you have polarization information, for example, from baseband data, we can study the Stokes parameter of FRBs. Here are beautiful examples of IQ UV spectra from SCAP of 4 different FRBs. From the 4 Stokes, we can derive polarization information of FRBs. Here are some examples of polarization profiles and dynamic spectra of 7 bright bursts from an FRB first discovered by Parkes and later followed up by FAST. The bursts here show a diversity of polarization properties. These bursts have high degree of linear polarization, shown by the red line, and no obvious circular polarization, shown by the blue line, which is very similar to the story of R1. But at the same time, this particular repeater shows a rich diversity of polarization, position, angle, PA swings across the pulse profile, which was not the case for R1 or R2. As the linearly polarized emission travels through the interstellar medium, in the presence of magnetic field, free electrons along the line of sight lead to Faraday rotation of the observed radial emission. The differential Faraday rotation, or the change in polarization angle between 2 observing frequencies, is associated to the rotation measure and the observing wavelength. This rotation measure, RM, is analogous to dispersion measure, DM. And techniques such as QU fitting and RM synthesis can be used to determine the RM. The plot on the left compares the RM and DM of pulsars, the black dots, with fast radio bursts, the magenta triangles. Currently, the highest RM record is still held by R1 at 10 to the power 5 units. Most of the RM measurements came from repeaters because it's easier to trigger baseband data when you know where to look. However, there are also some one-off FRBs that have polarization data. Two things I'll note here is that intra-channel depolarization can wash out very high RMs. It is also possible to have temporal RM variations, for example, in the case of R1, and I'll refer you to Hilarson's talk in plenary session 3 for more detail. With multiple repeated bursts, we can look also for any clustering in time and the energy distribution of the bursts. Here is the plot of a number of repeaters discovered by chime, showing when the burst was detected, and the signal to noise is represented by the size of the circle. We can see by eye that these repeaters have some temporal clustering, so that when one burst happens, it seems to be more likely to get another one. So far, 2 repeaters have been observed with periodic activity. This plot here shows the one discovered by chime, and it is R3, which has a 16-day activity cycle. This is my last slide. You'll be able to see, to find these parameters we talked about on public databases, such as the TNS and FRB stats for all currently published FRBs. In general, high time resolution data, preferably microsecond sampling time, is important for quantifying burst properties. The best is definitely baseband data when it comes to localization, polarization, and microstructure analyses. Wide instantaneous frequency coverage is useful to study drift rates and frequency range of FRB emissions. And we should also be mindful of any potential instrumentation effects and selection bias when analyzing these parameters. I'll leave my email here. Feel free to contact me if you want to discuss any of these FRB measurements in more detail. Thank you for listening and enjoy the FRB 2021 conference.